All right, so we have to talk about some pressures in order to understand what's happening at the capillary bed. Um, all right, so we have capillary, arterial end, venous end. All right, somewhere down there outside is the heart, right? Pumping blood, pushing it through this capillary. So it means that inside the capillary, we have a hydrostatic pressure. Capillary hydrostatic pressure, or capillary pressure as we put it in this point. I prefer hydrostatic pressure. That's just not what my diagram from the book shows, just because it's easier to understand. So the heart has hydrostatic pressure that's entering the capillary. Now the direction of forces is going to be huge to understanding here. So the hydrostatic forces inside the capillary are pushing out, right? So there's more pressure inside than there is outside. Okay, so that's pressure number one, capillary hydrostatic pressure. Pressure number two, plasma colloid osmotic pressure, which we talked, was that in this class or PATH? One of those two, we talked a little bit about it. So blood has a lot of stuff dissolved in it. High osmolarity. Osmolarity pulls water towards it, right? So osmolarity creates a pressure, an osmotic pressure. In our bodies, we call that plasma colloid osmotic pressure. That's an inbound pressure that's pulling fluid from everywhere else into the blood because of all the solute that's present, right? Okay, so that's an outbound and an inbound, both from the blood. We haven't even talked about the tissues yet. Okay? Now, on the tissue side of things, we also have a tissue hydrostatic pressure, right? That, in other words, there is some degree of pressure in the interstitium because the skin, for example, isn't infinitely stretchy, right? If you put 10 cc's of fluid under the skin, the more volume you put in, the higher the pressure is going to be because the skin was trying to get rid of it, right? So our interstitial fluid pressure is an inbound force. This is the pressure of the fluid in the tissue trying to be pushed back into the capillary. Then we have a matching interstitial fluid colloid osmotic pressure. The interstitial fluid also has a bunch of stuff dissolved in it, okay? It is also that stuff dissolved is going to tend to pull fluid towards it. So we have an outbound and an inbound plasma caused pressure, and then we have an inbound and outbound interstitial pressure. So you can imagine that a balance is coming up here, right? Where we're going to take the outbound pressures and the inbound pressures, and we're going to sum them up, and we're going to see, all right, what is the net filtration pressure? What is the net amount of pressure pushing fluid out or pulling fluid in? Okay? So, hydrostatic, capillary hydrostatic, plasma colloid, interstitial colloid, and then interstitial hydrostatic pressure. Okay, one more thing to add. When we take fluid and pass it through a pipe, all right, remember each little bit that it goes through the pipe, it's encountered resistance. So the hydrostatic pressure at the end of the pipe is lower than the hydrostatic pressure at the beginning of the pipe, right? Because the resistance has taken it up. This is true in our vessels too. As blood passes through the capillary, it loses energy. So we have a higher hydrostatic pressure at the beginning than we do at the end. All right. So because of that, more fluid exits early on and more fluid enters the vessel later on. All right. So this is actually one of my favorite diagrams for this concept because I think it very clearly shows you the important bits. All right. So arterial, venial, capillary. Hugely simplified, right? That's not what a capillary really looks like, but we'll move past that. Okay, so at the beginning of the arteriole, we have a lot of capillary hydrostatic pressure. That's the big outbound pressure there, right? The inbound pressure, the blood colloid osmotic pressure, is about 25, right? So we have 35 out, 25 in. Now, of course, you're going to ask me, well, what about the tissue pressures? We are ignoring them for this diagram, okay? You can take all of those pressures, like you can add the two, let's see, what are the two inbound pressures? You can add the interstitial fluid pressure and colloid pressure. You can add the capillary and interstitial, and you can subtract, and then you'll get this, right? So we're just simplifying it for this point. So capillary hydrostatic pressure out, colloid osmotic pressure in. That gives us a net filtration pressure of plus 10. All right, what the heck does that mean? It means that that fluid is going to tend to leave the capillary at the beginning because the hydrostatic pressure is greater than the colloid osmotic pressure pulling it back in. So you have more out than in, it goes out, right? Now, as fluid goes out, the hydrostatic pressure falls a little. Also, as blood moves across the tube, the hydrostatic pressure falls a little because of resistance. So by the time we get to the middle of the capillary bed, we have a balance. The hydrostatic pressure is exactly offset by the blood colloid osmotic pressure. So we have effectively no movement, right? Blood isn't, or water, fluid, isn't flowing out or in. Now at the end of this vessel, where we've lost a lot of our hydrostatic pressure across the path here, now we see the reverse of what we had at the beginning. We have our hydrostatic pressure is down to 18, our colloid osmotic pressure is 25, so now the difference is -7 pulling in. So now we have a net flow of fluid into the vessels primarily because of colloid osmotic pressure, right? So at the beginning, we have outbound. At the end, we have inbound. Now, if we look at the numbers, this accounts for about 24 liters per day being pushed out. The pull in is 20.4. Okay, so there's a difference between those two, right? 3.6 liters, a fair bit of amount of volume. Where does that extra fluid go? Anybody know? Lymphatics. Goes into the lymphatics, and then the lymphatics drain that back into the to the blood at the thoracic duct and the right lymphatic duct. All right, so this is net movement of fluid, right? So this is fluid movement. I like to call it bulk flow, where you're moving water and solute together. Diffusion is moving solute alone through a fluid medium, right? So this is really talking about bulk flow. All right, so a couple of key terms. Capillary hydrostatic pressure, for sure you need to know. Blood colloid osmotic pressure, for sure you need to know. Difference between those, net filtration pressure, okay? All right, so if we take all of the forces together, okay, remember this is just including the plasma forces, but if we include the interstitial forces too, okay, then we get what's called the Starling equilibrium. Not to be confused with the Frank-Starling relationship, okay? Same guy, Dr. Starling, different discovery, okay? So Frank Starling, remember, is as EDV goes up, ESV goes down. The Starling equilibrium discusses how we put all of these forces in play at the capillary bed all together at once. Okay, so we have our outward forces, capillary hydrostatic pressure, right? Interstitial fluid colloid osmotic pressure, so this is the pull of the interstitial fluid because of its solute. And then we have the interstitial fluid pressure. Now, here's where it gets a little interesting. You'll notice that that is a bit negative, and that is actually what is true. So the interstitial fluid pressure is usually not positive. It's positive in swelling and edema. Normally, it's a little negative, as we see here. So if we have a negative interstitial pressure, that's an outward pressure. So we can add all those up, we get 28.3. Okay, now what are our inbound pressures? In other words, being pulled in towards the blood. Plasma colloid osmotic pressure is the only one, right? Because the interstitial fluid pressure is negative. So it's working for the other team. So all we have as an inward force is colloid osmotic pressure. So if we line those two up, we can see that we have a relatively small net filtration pressure of 0.3. That is still not zero, okay? You're still going to get a fair bit of fluid more out than in. About 2 mLs per minute, okay? So that's the lymphatic system. There's plenty of examples. If we don't have a functioning lymphatic system in an area, that area will continue to get more and more fluid developing in it until it grows new vessels if it can, new lymphatics. Elephantiasis, they call that, is when you have like a body part that's hugely lymphatically swollen. All right, so some capillaries have a big net flow, some have less. So generally speaking, in brain and muscle both like to be a bit on the dry side. So we get very little net flow. In other words, our Starling forces are well balanced in the brain. In the intestine, though, we get and in the liver, we get a much bigger difference. So we get a much larger bulk flow. This is useful in these places because moving fluid is also moving solute, right? And like in the digestive tract, the whole point of the digestive tract is to move solute into the body. So being able to move it in bulk works a little bit easier than having to do it through diffusion. Now the other thing that varies is the interstitial fluid content. So like the colloid pressure generated by the tissues varies according to which tissue you're talking about. Some tissues, for example, in the medulla of the kidney, there's a very, very high interstitial fluid or interstitial colloid osmotic pressure to such an extent that it plays a role in urine concentration. So variance across the body. In other words, it's not always 28.3 and 28, okay? That's an example.